You can update your workspace to tag 02-mutated token, and you will immediately find the new stuff in the contracts folder. Let's start with the interface for the mutated token. As we saw with the mutation token interface, we have a bunch of error definitions so we can revert in a clear yet efficient way. We also have a mutation event that is worth some explanation. I decided to go with an implementation which differs from other ones that I saw so far. Let's take the Macy's collection as an example. You have a max supply of 3008 NFTs. The first 10k are new apes that can be minted. I'm not gonna replicate these features because that would create inflation that is out of control of the Genesis holders. As everything on this channel, this is just a personal opinion, but I don't like that. The next 20k are actually divided in two batches. Even IDs are for bases mutated with the M1 serum, and odd IDs are for bases mutated with the M2 serum. The last 8 Macy's are the apes created using the Mega serum. So the thing that I didn't like with this solution is that your collection is gonna have empty slots in it depending on which tokens get mutated and also depending on the type of serum that is used. For instance, Basie number 1 becomes Macy number 10,000 with M1 serum and 10,001 with M2 serum. But those IDs will be empty if that Basie doesn't get mutated. Also, reserving token IDs like that doesn't even have the advantage of a perfect match of IDs between the two collections. For example, it could be 10k for M1 and 20k for M2. They probably had a very good reason for this, but I find it kinda messy. Last but not least, if you want to protect your metadata and images so people don't know how their tokens will look before mutating, then you still need a backend for that. So the main advantage I see is less data stored on the contract, but with the trade-off of a messy supply. My implementation tries to solve this in a different way. Mutated token IDs start from 1 and go up as new tokens get mutated. This means that lower IDs go to people mutating earlier, which is also something people really like. The contract state will hold data about which token was mutated and what type of serum has been used. External services will be able to query the contract in order to get that information and react accordingly. Back to the mutation event, this is really useful because we can listen to it in order to generate the mutated tokens and make the metadata and images available publicly. As you can see, the event contains all the information we need: the Genesis token ID, the mutation type, the mutated token ID, and the owner address. Of course, reactions to this event will happen off-chain and have nothing to do with the contract itself, but this has to be planned up front. The token data struct holds information about each token mutation, the Genesis token ID, and the mutation type. This will be used in the contract state. The mutation status struct will be used in order to return information about mutation for a specific Genesis token. This will be used by the dApp. In this case, we need the Genesis token ID and a Boolean array that contains whether or not the specific token has been mutated with each mutation type. Now it's time to check out the implementation. Here it is. I'm importing some stuff from dependencies as well as our interface. The contract implements our custom interface and also extends ERC721A, Ownable, and Reentrancy Guard. We talked about the last two in the previous video, and I assume you already know the ERC721 implementation by the Azuki team. The only constant value is the number of mutation types. This should reflect the number of token types managed by the mutation token. As we learned in the previous episode, immutable variables allow us to change their values at deployment. In this case, we need to access both the Genesis contract in order to verify ownerships and the mutation contract in order to manage its tokens. The URI prefix and suffix will be concatenated with the token ID in order to return the token URI. It's not mandatory to set them here because we can always use the setters later. This Boolean flag pauses the contract by enabling and disabling the mutation. Token data uses the struct defining the interface in order to map the mutated token ID with the related information. As being mutated is a map to an array of Boolean values, one for each mutation type. This stores whether a genesis token has already been mutated with a specific mutation type or not. The constructor simply initializes the ERC721A contract and sets the references to the genesis and mutation contracts. The mutate function gets a genesis token ID and a mutation type, and it's non-reentrant. We always follow the checks, effects, and interactions pattern, so first of all, we check all the conditions and revert in case we find anything wrong. Mutation must be enabled. Mutation type must be valid. The sender must be the owner of the genesis token. The sender must also own at least one mutation token of the correct type. And last but not least, the genesis token must not have already been mutated with the given mutation type. If everything is fine, then we can update the state. We set the mutation status to true, and we add the token data entry for the new token. We can now emit the mutation event and do our interactions, burning the mutation token and minting the new mutated token. getMutationStatus is a utility function which is meant to be used on a dApp. We make sure the token ID exists, then we return the corresponding mutation status. Wallet mutation status is pretty much the same as wallet claim status from the previous video. We simply return a mutation status instead of a claim status. Next, we have three simple setters for our variables. Please pay attention to the only owner modifier. We already saw the token URI function in the mutation token contract. This does exactly the same thing. I know a lot of developers will disagree with this, but I like collections to start with a token ID of 1, since this number is exposed to the user. I'm also implementing ERC165 in order to explicitly support our own interface for correctness. As you can see, the code is not extremely complex. What's more challenging is planning how everything should work together, including the dApp and external services, so we can provide a smooth user experience.